Hello friends, today we will discuss about the limitation of conventional tubes at higher frequency levels. The triode, pentode, tetrode are the conventional tubes. These tubes are only useful at low microwave frequency, which is about 100 MHz. The vacuum tube was the first active electronic component which is capable of actually controlling and amplifying the small signal. It was invented in 1907 by D. Frost. The basic elements of the vacuum tube can be shown in the schematic diagram of vacuum tube. Now we see the functioning. The filament heat up from the applied of AC and DC voltage and is caused the surrounding cathode to emit electron. Anode plate is charged up and high positive DC voltage attract the electron emitted by the cathode. Due to flow of voltage, the electron between the cathode and anode, the plate current gets generated and the amplified output is produced across the load. The load may be antenna, filter, modulated or demodulated circuit. The intermediate component between cathode and anode plates is grid, which is used to control the flow of electron by varying the voltage. When the grid voltage is varying from 0 to negative, then the large flow of electron between cathode and anode is controlled and modulated. Small vacuum tubes were available for microwave and millivolt signal but have been replaced by transistors. The size of electronic device required for generation of microwave energy become very smaller at microwave frequency levels. Because of smaller size, these devices increase the noise level and the result in lesser power handling capacity. So at the microwave frequency, the microwave tubes are used because they can provide the higher output power, lesser noise, better reliability and reduce the power output levels. We have certain limitation in conventional tubes. First is interelectrode capacitance, second is lead inductance, third is gain bandwidth product limitation, fourth is transient time effect, fifth is skin effect, sixth is dielectric losses. Now we will discuss all of these in detail. First we have interelectrode capacitance. It plays an important role in the operation of tubes at microwave frequency. It is due to active parts of tube structure between the lead. At frequency increases, reactance of CGP and CGK and CPK decrease and begin the short circuit at the input and the output voltages. This leads to reduction in amplification. These capacitance must be minimized. It can be achieved by the increasing the distance between the electrodes or reducing the area of the electrodes. The second limitation is lead inductance. The leads have small but finite inductance. When the frequency increases, the reactance of this become appreciable. They limit the performance of the tube by providing degenerative feedback. They can be minimized by the short lead tube. By the formula of lead inductance, you can see that capital L is equal to small l over mu into A. To decrease lead inductance, increase the area and decrease the length. The third limitation is effect of transient time. The time taken by the electron travel from cathode to anode is known as transient time. At lower frequencies, the transient time is very small. That is, the electron reaches instantaneously to the anode plate from the cathode. At higher frequency, the transient time becomes very larger because the source driven the grid becomes overloaded and the gain of the vacuum tubes becomes less than unity. At smaller frequency, transient time is very less. In that case, IP and VG are in same phase. IP is plate current and VG is grid voltage. But at the higher frequency, the IP and VG are different in phase. And in this case, the voltage is changed from negative to positive 1 to 100 times in one cycle. This loading is due to the dissipation of power and the grid. This effect is loading is such that the noise in the circuit is increased. To minimize this effect, the distance between the electrodes is to be reduced. At the higher voltage, must be applied. Now see how the transient time will be calculated. From the definition of transient time, we know that tau v is equal to d over v0, where v0 is the velocity of electrons. The static energy of electron is ev. Kinetic energy of the electrons, which is given by ev, given by half mv0 square. We note that the under equilibrium state of the static energy of electron, which is equal to the kinetic energy of the electron. By the equating these equations, we obtained v is equal to 1 upon 2 mv0 square. From this, v0 gets equal to the under root of 2 ev over m. Substituting the v0 value in the equation, tau is equal to d over v0, we get tau is equal to d over under root of 2 evm. This is the transient time equation. The fourth limitation is skin effect. This effect introduces at higher frequencies when the current flow from the smaller cross-sectional area to outer surface of the conductor. At the frequency increase, the resistance of the conductor increases. Due to this, higher frequency losses are produced. The skin depth delta, which is inversely proportional to the square root of frequency omega, and it is also proportional to the effective area. By this sense, the effective area, which will be inversely proportional to the square root of frequency. Resistance, which is given by the relation R is equal to rho L over A effective, since the R is equal to rho L into square root of frequency. So as the frequency increase, the resistance will also increase. By this, the higher frequency losses are produced. Our next limitation is gain bandwidth product limitation. To achieve the maximum gain, the vacuum tube generally use this circuit. This is LR circuit and V0 is the output. The R net, which is given by 1 upon Rp plus 1 upon RL. The G, which is gain, which is equal to the output voltage over input voltage. And the inverse of 1 upon Zs, which is given by Cs plus 1 upon Lr plus 1 upon R from this circuit. By calculating, we get S square Lr plus Ls plus R over Lrs. By solving this, we get Zs equal to S over C over S square plus 3S over Cr plus 1 upon Lc. This is equation. From this equation, the denominator, the roots given the values of largest and higher frequency order, which is given by omega and omega n. Omega n, which is given by this characteristic equation, minus g over 2c minus under root of g over 2c ka whole square minus 1 over lc. Omega n, which is equal to minus g over 2c plus under root g over 2c whole square minus 1 over lc, where g is the conductance, which is the reciprocal of resistance. G is equal to 1 upon R. And the bandwidth, which is by omega n minus omega 1, this is the difference, which is equal to g over c, where g over 2c is whole square, which is very large than 1 upon lc. Then we can write A max, maximum gain, which is given by gm over g. Then the substituting the value in the gain bandwidth product becomes g over g cross product with g over c. The cancellation of capital G, we get the gm over c, where c is the capacitor. And finally we get am, which is the maximum gauge, which is inversely proportional to the bandwidth. This relation is independent of the frequency. To achieve the higher gain, we need to bandwidth lower, and the higher bandwidth, the gain gets reduced. This is also known as gain bandwidth product limitation in conventional tubes. Our last limitation is dielectric losses. Dielectrics are the different insulating materials which are used as glass envelope, silicon, plastic encapsulation in different microwave devices. The loss in any of these material in general relate to the power loss. P, which is power loss given by pi f v square sigma tan sigma, where epsilon naught is the relative permeability of dielectric, whereas delta, which is loss angle of dielectric, P is power loss. At higher frequency, the power loss increase. To eliminate these losses, the surface area of the glass should be decreased and the tube base should be eliminated.